is 60% weight ethanol, and I'm feeding 1,000 kilograms per hour. I know that this feed is a mix of liquid and vapor, and that is at 81 Celsius. I have a second feed that is 10 weight percent ethanol. I'm feeding 500 kilograms per hour, and I know that this feed is a liquid and it is at 20 Celsius. I want to achieve a bottoms composition of 0.01 weight percent, distillate 85 weight percent. I know that my column is operating at a constant pressure of 1 kilograms per square centimeter and is adiabatic. I know that I have a reboiler and a condenser. I know that the distillate are saturated liquids. And I want to find the flow rate of the bottoms of the distillate. I want to find the cooling load for the condenser. I want to find the heating load for the reboiler. I want to find these amounts or these flows of heat and mass for the case when I have an external free flows ratio of L over D equals to 3 in mass units. And if I have a boil ratio of 2.5, also in mass units. So how this look like? So I have a column, right? And I have 2 feet to that column, right? I have here the vapor that goes to the condenser, and I want to calculate, this is one of my hormones, that heat load, right? And here I have the reflux. This. And then here, the bottoms, the fraction, and this is the other amount I want to know. That is QR, that heat load, that boiler. So as we learn in this chapter, the first step that we need to do at this point is the overall mass. Overall mass, remember that in this chapter we are focusing on the overall mass balance and energy balances on the whole column. Chapter 4 is individual balances for each stage. So let's do the overall mass balance. And the overall mass balance is the feed, but in this case we have 2 feeds, right? Equals the bottoms plus the distillate. We are going to do also a most volatile component mass balance. So that allows us to have 2 equations. Again, we have 2 feet, right? So that's why we are doing adding 2 times this equals the bottom, the fraction of the bottom, distillate, the fraction of the most volatile component on the distillate. So we have these equations. Now I'm going to modify equation 3.3 I provide you in your notes for the distillate. It's one of the equations I provide you in one of the classes before, but I'm going to modify it. So modify it for 2 feet, because that's a kind of interesting part of this problem. We are having 2 feet that we need to include in our balances. So if you can please take note, that's visible, right? If you please can take note. So I'm gonna put everything in and see average. So that's a modification, guys. I'm putting an average composition of the most volatile component in that C average, and I'm putting an F total that is the sum of the 2 feet. So we are again just modifying equation 3.3 for 2 feet. So if you want to take note of this equation in case you deal later with a similar problem, that would be good. Where F total is going to be what? Yes. F1 plus F2. So F total, F1, 1000, right? Plus 100. So at this point then we can calculate the C average. So let's get C average. So going to be 1000 times 0.6 plus 500 times 0.01. And these are given, those are the fractions. Given F total, we said that it was 1500.
Is the bottom C total or F2?
Yeah, it's a fraction. So it's the sum divided by the total.
I'm sorry, I'm just confused because it says Z total, right? But
Yes.
the number you wrote is...
This is F1, yes, sorry. Is the sum of the fields
Okay.
divided by the total.
It's F2.
Yeah. So how much is that? And I didn't put C average and C average. So you can calculate that C average and also the distillate mass flow rate, because you have now F total that we calculate here. We are calculating the average, that is the value that we are obtaining here, and then we have everything ready to put into this formula. So you can give me the average and also the distillate mass flow rate.
This 0.4.
0.4. I have a calculation 0.433. 1000.6 point. How much is the fraction? I think I have another calculator. Yeah. Yeah, you might be fine because this is a fraction. This is C2. How much is C2? C2 is 10%, right?
Okay.
Yeah.
Okay.
Yeah, this is a data for me. I can bring back the problem.
Okay.
So C1, first feed is 60% ethanol, 1000. Second feed is 10% ethanol, so 10 divided by 100 is 0.1. So it is 1. Because of 0.01. So how much is the distillate then? So distillate is gonna be that formula. That is the average minus ZB. If that's 0.0, this is 0.01. This is XB. That is for the bottoms, and that for the bottoms is still 0.01 weight percent. So if you divide it there, and this is the same as this one, XP, and this is the distillate, and the distillate is 80 weight percent. Everyone is getting the same values? So now we can get B from the overall balance. So how can we get B? The bottom. That's the question. Bottom is
B minus D.
B total minus these two. Yes. So F total, we said that is 1500, and the distillate we just got it here. So it was 6764, and that's the bottom. So we have now defined the flows, the mass flow rates for our column. We know the feeds, we know the flow of the distillate, and we know the flow of the bottom. So by general balance and the most volatile component balance, we were able to obtain those three currents. So we have found those. We need to find now the heat and cooling loads for two cases. So we need to find the heat and cooling load for QC and QR for an external reflux ratio of 3. And this we have done in the past. In the example we did last class, I guess. So how we can find heat loss? With the energy balances, right? So we need to go back to our equations for energy balances for our column. And one of those equations is equation 314. Well, we know that the heating load for the condenser is 1 plus L over D. D, this is a D, HD, HI, so the enthalpy differences. So I think that the problem suggests also the same thing to use figure 2.4. So I ask you to please bring your book. So I need that you locate function value. Please. Why? Because as you can see, our energy balance is indicating to use enthalpies, right? And for that we need function value. So let's go to figure 2.4, please, in your textbook, and I think I can put that in use. Should be D1. Yes. And I need that you read the enthalpy for the distillate, and we know that the fraction is 0.85, and we know that we are dealing with a saturated liquid. So you need to read for a fraction of 0.85 and the saturated liquid line to get that enthalpy of the distillate. And for H1, right, we know that for this case, based on assumptions, right, the distillate equals Y1 because we are not changing anything, right, but the phase, the fraction remains the same. So since we are changing the phase, we need to read for a saturated vapor. So I need that we read those values and then you know how much you get. Do you see my contours are right here? I can make it a little bit more. So 0.85 is around here. I go up, right? This will be the liquid, the saturated liquid line. And if I follow the same procedure and go up, I can read here, right, the saturated vapor enthalpy. Remember, this line, bottom line is saturated liquid, top line is saturated vapor. Any lines in between means that we have liquid vapor composition.
We were at, I think it was 80 degrees Celsius and then at 20 degrees Celsius. How would the question be stated if we use the temperature in account?
Yeah, but we haven't reached that part.
Oh, okay.
That is for, I mean, you are talking about once we move to the reboiler.
Okay.
In that you will have the temperature there element, and that's why I have the other readings here. We will do a reading for that mass balance at around 80 if you want to.
Okay.
So that's for the reboiler, very the comments.
Okay.
So as you can see, one of these are my readings. I don't know how much you have troubles in reading when you stop by. No? Okay. So I read. So can you get me QC of the load for that condenser, please? So please solve for this with equation 314. Let me know how much you get. You have already the enthalpies, and we are given this ratio of L over D equals 3. I'm going to put my numbers here so you can compare. So 1 plus 3. And we calculated in the previous page the distillate. So it's a big number, minus 80, 90, 80, or so kilocalories per hour. Does anyone have something? Yep. So well, we solved that amount for the condenser. Now we need to make a whole balance in the entire column to get the other. So let's solve now. Then for the heat load, for the boiler, and for that we have to record our energy balance around the column equation. And we did this general mass balance, so, but we have to do it for 2 feet, so it's just a matter of putting an extra FH, right? We said that we will assume that our column is a level condenser, reboiler, and then the distillate, and then water. So this would be our overall energy mass balance. And as you can see, well, it contains the other amount that we don't know. have defined the condenser, we know the feeds, we just don't know maybe some amounts of the distributed voltage, right? So let's go back to Poncho's summary for the missing enthalpies. So from figure 2.4, read the missing enthalpies. So we know that we have one feed, feed 1 has a fraction of 0.6, and we are feeding at 81 Celsius. We know that we have a feed of a second feed with a fraction of 0.1, and we are feeding at 20 Celsius. And so I need that you guys read for me these enthalpies. And we know, we don't know the bottom, and this is a bottom. So all the time these guys go this design, so the float and the enthalpy, the float and the enthalpy, so it should be the same. I put a D here, now it's B for bottom. The bottom is a saturated, what we have in the bottom? Liquid or vapor? Liquid. So you need to read in the liquid, saturated liquid. And approximately we will have 0% ethanol. Why? Because all the ethanol is where? Here, we are feeding 0.6, so 0.6 and around 81. So here is the 81 temperature line, right? So again, 0.6, 81, go, and I can read that feed enthalpy. Then I have the second one, so I have a fraction of 0.1 and I'm feeding at 20 Celsius. And this is kind of tricky because this is at 20 and the lines are not good. So okay, 0.1, 20, go, here. And the other one is 0% ethanol, right? So remember Poncho's summary. So we will have 100% ethanol here, 0% ethanol here, because it is made in terms of the most volatile component. That's something that you need to have in mind in separations. Everything, most of the data is given for the most volatile component. So this guy or this Poncho's summary is built in terms of the ethanol. So 0% ethanol is here. So we have 0% ethanol, and we have to here to go to the saturated liquid. So HB is going to be this value of around 100. Okay? So 0% saturated liquid, remember is here, saturated vapor on top, and any line in between means that you have vapor liquid. Okay? So my values, again, do you need time for reading that? I need to check. So F1 is around 190. Then MHB 100. So I think we can solve the overall mass energy balance of it to get QR. So we can do that. And that's how we obtain the heat load for that. So again, we have everything. Please solve for QR, the heat load for the boiler. So this procedure is kind of a standard, guys. It's what I want that to visualize, and maybe next problem I will let you do alone. General mass balance, then the balance for the most volatile component, then just do the balance either on the reboiler or the condenser and move to general mass energy balance. And that completely specifies your column in terms of mass and heat loss. So I got a value. 7 to 820. So we solve for an LD or external flux ratio of 3. Now the problem says what happened to these heat loads if you have a boil-up ratio of 2.5. So with a boil-up ratio of 2.5, what are the loads? How much heat you need to input in that condenser and reboiler? And that's the main idea that I wanted to visualize with this problem, that by changing these very important amounts that are the L over D ratio right on the top of the column, and also the boil up in the bottoms of the column, you can change those heat requirements. And well, your job would be to minimize them because that's cost, right? Or maybe look into your process which current might be hot enough to provide that, right? And make it more economically feasible. So let's now repeat the problem for this. And for that, well, for the bottom, in this case, we need to make a little diagram. And I'm pretty bad to make diagrams. So for solving for this one, since the boil-up ratio deals with the reboiler, let's look at the reboiler. And I'm going to separate the reboiler here. So let's break the problem then and focus on the reboiler when we work with this boil-up ratio. And let's do this energy balance in the reboiler first. That can help us to specify warm heat, this current of the saturated vapor, B, and of L, the saturated liquid. Okay, so let's make an energy balance on the reboiler. So if you look at my drawing, all we have to do, in equals out, right? Is all I'm doing. Let's pair with a mass balance, because we have some common variables. And I know that B, the vapor, is 2 times the bottom, right? That's what we define in here. That's what the formula is. B, 2 times. That's how we relate the saturated vapor with the bottom. Last bit, because we have an extra bit here, the bottom. So we know that the saturated liquid L equals 3.5 B, the bottom. So 3.5 times the flow rate that we calculated for the bottoms, and we already calculate in previous questions. Right, we have L value here of the saturated liquid current to our reboiler of 25.6 kilograms per hour. So we define this one, we know the bottoms, we can know this one. So let's get the saturated vapor, please. And let me know how much you get. So we can get the saturated vapor. It's going to be the saturated liquid minus the bottoms. And we just got saturated liquid, right, from the boil-off ratio that we are given. As you can see, it's just mass energy, mass energy, mass energy. And essentially, this is what you have to do for your exam to show me that you can do mass and energy balances around a distribution column. So, how much you get? So I need that you look at the reboiler image that I made there. And we know that approximately the fraction of the liquid, bottom fraction of the liquid, is that of the vapor and is that of the saturated vapor, right? So then we can know the enthalpies by relating to one another. So here is B, here would be, so that's B, this is going to be the vapor fraction, and this is going to be the liquid fraction. So they are approximately the same because we are not doing anything, it's just a reboiler, right? But the fractions, the composition remains the same, it's just a heat transfer process. We are just transferring heat, energy. But the compositions, what happened to them? They're the same. So we can approximate with this is equal to this, this is equal to this. That is what I'm doing here. Equal, equal, equal. It's just heat transfer, just energy transfer. Not changing anything in compositions. And that means that I can relate that to the enthalpies, right? So let's write the enthalpy that we might be missing. And I think that value we have read it before. Can someone get it back, please? Yes, right? Thank you. And we need to read the saturated vapor. And in function summary, so again, figure be saturated vapor, so that means that I have to read up there. That's the saturated vapor line. So it's that one. And it's above 600, so 640, 645, 650. So I think we are ready to get QRs out of the energy balance for the reboiler because we have defined this one somewhere here, here. We have HL, right? That is that one that we approximate, right? Because of the compositions of the reboiler. So again, this is for the case when we change the boil-up ratio. So from here we have defined everything from the energy balance for the reboiler. So please get QR. Let me know how much you get for this case. And I can put my numbers. QR from reboiler energy balance. So you have the balance there, right? So QR equals VHG voltons, and that will be voltons, saturated with VHG. And well, we got 840, 640, plus 736, 100, 25, 76, 100. So I got 993, 600 kilocalories per hour. That differs from the other case where we change L over D, right? So there's an impact of the boil-off ratio compared to LD in these heat requirements. The next step that we can complete next class is just to go back to the overall energy balance. We already have QR, so we can calculate QC. So it's more or less the same procedure we need to follow. Okay, so next class then we calculate QC with total energy balance. And that's it, that would define or complete the problem.